the idea of eBPF and making the kernel programmable was immediately super interesting. This is gonna not only change what we were working on right now, but it will also change the industry forever. In 2011 was exciting. All of us working in the kernel field, we just went through this like amazing growth of Linux. We built features and features and features, and Linux was winning.
Linux became so successful that it's being run on all the hyperscalers on billions of devices, from smartphones even to the Mars helicopter nowadays, and it's really just one source code base.
Most people involved in eBPF later on, we were all working on network virtualization, software-defined networking.
SDN was kind of the hype du jour, which is software-defined networking.
Software-defined networking was a really hot topic. People were thinking about how they could connect workloads using software rather than connecting things with physical cables.
What used to be a hardware business, networking, became a software business.
We were all trying to solve this same problem, which is how do you move packets around in a data center when there's a lot of virtual machines sitting on servers and the server takes a prominent role in the packet forwarding.
SDN by then had already become quite mature in terms of standard virtualization and supporting different feature functions, networking, security.
However, there was not really this flexibility of programmability. It wasn't taken to another level.
The technology available in the Linux kernel at the time was really focused on bridging or Ethernet switching, which was not necessarily the right tool for the job.
At the time, the industry was actually getting a little bit stale. We needed something to take things to the next level.
Linux was everywhere, but this also meant kind of a huge, massive pressure on everybody that Linux was supposed to become boring, stable. So there was a natural enemy to innovation.
If we go back to kind of where we were at the time, well, I was at Red Hat. I was an engineer working on SDN. In my role as kind of the architect lead for defining what SDN meant for Red Hat, I had the opportunity to talk to a lot of different companies that were building these solutions, some open source, some proprietary, to do SDN work. And one of these companies was Plumgrid.
Plumgrid stands for Plum, parse, lookup, update, modify. And the main idea of the startup was a collection of these plums or plumlets that were connected into the grid, and they would be performing a networking function. The idea was safety of the loaded programs into the kernel by the language and by the compiler, similar to what Rust as a language is doing now. I believed in it until we hit a bug where after several hours of networking traffic, the host would be crashing. And at that point, like something clicked. I realized that the compiler, you cannot trust the compiler, the kernel itself. When something gets loaded in the kernel, it shouldn't be trusting the user space. So that's how the verifier came about. The kernel has to be able to verify what is being loaded into the kernel. So since I had to change the compiler, I figured, well, I will just invent my own instruction set. But that's not the eBPF yet. It was just an instruction set where we just reduce, it sort of was like reduced x86 instruction set. What's remarkable is CEO and CTO of Plumgrid at the time, Avais Nemat and Per Monklus, they knew that for a technology to be successful, it has to be not only open sourced, it has to be upstream. And it was clear that the new instruction set, it's going to be huge, right?
Plumgrid had this notion of a more flexible way of moving traffic around in the server. Alexei flew up to Portland, where I lived. It was one of those kind of mind meld moments. How could you insert right into the Linux kernel kind of a a probe point that would capture a packet, give it to the small program that could look at the contents of the packet and then make a decision of what to do with that packet. It turns out that that concept is much more general than just networking. It actually creates this ability to truly extend the kernel in ways that researchers have been trying to figure out forever. That is really fundamentally changing what we can do with Linux.
He was brutally honest that for something like it's huge like this to land, people should not see it as a revolution. The only way the kernel community can accept something like this if it's similar to what already exists.
Alexei, we need to extend the Berkeley Packet Filter.
At that time, he pointed at BPF. His suggestion was make it similar to this. So I came back and started redesigning my instruction set to BPF-like. And to make it similar, I had to keep name BPF, so I called it extended BPF because why, what else? I was pretty much uglifying the instruction set I had to make it similar to classic BPF. So I've posted my first patch and no one looked at it. One person just asked some silly question, but there was no action.
I was just going about my day-to-day affairs, applying patches all day, some bug fixes for drivers, random stuff. And then suddenly I see this thing that's gonna somehow enhance what I'll refer to as classical BPF, which is the existing BPF mechanism that existed before eBPF. This really opens up Pandora's box in a way, because users could implement whatever they want in the kernel, basically. And this is going to be a support nightmare for anyone who sells distributions or enterprise support for Linux, because it's wow, what magic programs do you have executing alongside all the usual things? How do you provide support for that? It's a complex problem. He was trying to kill 1,000 birds with one stone.
Back at Red Hat, I was working already on the old style BPF. One day, this patch proposal has been sent to the kernel mailing list. It was a huge patch bomb, and it even contained an LVM backend, and to merge something like this into the kernel would have been crazy. I thought to myself, I was really fascinated by this idea. I really saw the potential and that this could be something big, right?
Daniel, I think he understood the idea, how powerful it can be, very quickly.
Daniel came into my office and said, "Hey, Thomas, I saw this patch set. This looks amazing. Can I work on this?" The idea of eBPF and making the kernel programmable was immediately super interesting. A million light bulbs went off when I saw that. We actually met with Alexei and we discussed how can we get this merged into kernel, because that was kind of the barrier we have to get through, right? In order to enable this innovation, we had to get the eBPF runtime into the kernel. We had to convince David Miller, which was the network kernel maintainer back then.
We went back to the drawing board and I told him, the most natural change we could do is to basically replace that old style BPF TCP-dump interpreter in the kernel and then to integrate the eBPF one and make it as a way that it improves its performance. So it's useful initially to even the existing users, right? So it's a small step-by-step change, even though the big idea is very revolutionary.
The major shift actually in perception of what BPF will be actually happened because of this hard pushback I had from the Miller and many others in the networking community, because the way we've created it was to solve the networking problem. They felt that OpenSwitch already solving all of the networking problem for them, so why second solution that was solving exactly the same stuff? So I had to come up with a second user for BPF. That's when we first met with Brendan Gregg.
So in 2014, there were some opportunities at Netflix where I could work on Linux but also as an end user of the cloud. I joined it thinking, this is a challenging environment. We don't have kernel tracing, we don't have hardware PMUs. I looked at all the Linux traces that were available and thought, I will have to get involved with these and get one of them fixed. The problem was there was over 10 different Linux system traces or kernel traces. And they were all about half finished. None of them could do everything that I needed to do. And so in my first couple of months at Netflix, I was getting experience. I was trying them in production. Then someone at Netflix says, hey, Brendan, did you see the email about BPF? A new one. I thought, not another one. Like, I'm already busy testing all of these other ones. Now, this was a patch set that was sent to the Linux kernel mailing list. And it was intriguing as the developer, Alexei Teretoyev, seemed to know what he was doing. He was breaking up the problem into parts and also talked about tracing as an implementation of a bigger solution. Now, one of my coworkers said he could probably get Alexei to come visit Netflix and talk to us about BPF. Alexei shows up, we grab a room, Alexei goes on a whiteboard and talks about BPF. I came up with an agreement in the Netflix offices with Alexei. If he were to add kprobe support, I would write all the front-end tools to use it from my prior background in Unix. And that was the first agreement.
And that's when I pivoted the whole thing into tracing. I repositioned the whole patch set, how I'm approaching upstreaming. When where BPF is going to be used as like, forget the networking, here's what I'm doing for tracing.
Early days of BPF, Alexei basically focused more on the tracing angle. I focused more on the networking side of things to make everything programmable there.
Daniel was helping me, so now it's not one person would be sending this big patch set with a bunch of features, but it was like 2 people. So when it's originated from 2 people, from Daniel and myself, it gave like a lot more confidence that once these changes emerge, somebody will stay around to support these changes.
I remember when I sent out this initial patch set together with Alexei, I was at the airport with my wife, and of course, like being a Linux kernel nerd, I had to check my phone because, when you send out patch sets, you want to know what's going on if somebody comments. And
the first submissions were just like, oh, this is just going to make the existing BPF stuff run better or faster. Okay, if it's just enhancing something we have already, why not?
David Miller finally hit the button and merged it. And he said, applied, thanks.
Merged, thanks, just one-liner. And it felt like monumental because we had all been working so hard to get that initial version in. And then like a one-liner was essentially the confirmation that it was finally done.
When it was merged, it was a huge celebration at Plumgrid.
And this was like the big moment where I told to my wife, oh wow, this is amazing, this could be something big.
It's been exhausting how many battles we've had to fight over the years to get BPF accepted. Because getting BPF into the kernel, it's this crazy idea. We're going to put a virtual machine in the kernel, in this dangerous space, and let people run programs in the kernel. This is like putting JavaScript into the kernel. This is a crazy idea. What Alexei did that was smart in those early days, instead of putting the entire finished Lego product into the kernel, Alexei was adding it Lego brick by Lego brick, and then slowly building it up. And when he began doing this, I don't think many people knew where he was going. Only Alexei knew where he was really heading.
It was probably 2 or 3 years between that initial patch being committed and people like me even hearing about eBPF. To understand the impact of eBPF in a cloud-native environment, we really need to think about how we've deliberately made our applications isolated from each other using containers and Kubernetes pods so they can run independently. But then that means if you want to instrument those applications, maybe you want to have common logging functionality or tracing or security functionality. How can we have a common platform that can instrument those applications in one go rather than having to do each one individually? And eBPF is the solution to that because it's sitting in the kernel. We can instrument the kernel, we can have these incredibly powerful tools that can observe and affect what's happening across the whole machine. That makes life so much easier from the perspective of an operator who's deploying those tools. It means application developers don't need to worry about how they're going to provide things like observability or networking capability, because eBPF's allowing us to build that in the kernel.
eBPF is fundamentally changing cloud-native space and the infrastructure software with that.
In 2011, 2012, and so on, like enterprise Linux was becoming the norm, right? Which actually meant that any sort of change in the Linux kernel took years to make it into the hands of end users. And eBPF changed that fundamentally again. All of a sudden, as long as the eBPF runtime is available, you can load a program at runtime. This means that all of a sudden you can have an idea, you can write the program, and you can get that into the hand of an end user running in the kernel within days. And when we saw that, we had almost kind of a panic moment. Well, this means we can rebuild everything better. What should we rebuild first?
Before joining Facebook, the growth of eBPF was mainly in tracing because of BCC toolchain and Brandon Gregg creating all of the tools, blogging about it, evangelizing. People were definitely excited about it. For Facebook, it was clear that just tracing abilities to understand what servers are doing, millions of servers at scale, will be hugely valuable. So I joined Facebook. Catran, the Facebook layer 4 load balancer, was created based on VPF and XDP technology internally to accelerate all of the packet processing inside Facebook. Within several months from its running in every server in the Facebook data center, we open sourced it through the GitHub. We made the blog post and presented it multiple times at different conferences. We showed BPF running in a data center with a line rate speed, processing 15 million packets per second, where BPF's program spends literally like 15 nanoseconds to process a packet. That 10x performance difference versus existing solution like APS was an eye-opener for many. The world saw what BPF and XDP are capable of.
Every packet that goes to facebook.com runs through eBPF at the XDP layer. That's really where the networking side for eBPF took off. Alexei, myself, and Brandon, Thomas, we gave talks about eBPF at conferences. And back then, I think they were like the hyperscalers were the early adopters, Facebook, Netflix, and they have their own kernel team that understood eBPF because it was so hard to use.
It's essentially assembly level technology, and you have to have deep understanding of the kernel itself. So it was great for the hyperscalers out there that have their own kernel teams to actually write eBPF programs, but it was not accessible for end users.
eBPF is so hard to consume, but at the same time, it was so powerful. It has so much you can do with it. Thomas and I, we had this vision that we should bring this not just to the hyperscalers, but also to the rest of the world. And that's why we initially then worked on Cilium.
One of the motivations why we've built Cilium is to bring the powers of eBPF to end users. So it was a small group of friends, 4 people. We wrote the first version of Cilium to build a completely new networking layer that was secure by default and would meet the scalability requirements and the performance requirements of containers. And then also bring in all of these new Kubernetes concepts where application developers and platform teams were operating it without actually wanting to understand the underlying infrastructure. And that was the design of the initial Cilium version. When we started building Cilium, I always had the idea of building a company in the back of my head. We decided to raise money and start Isovalent. We iterated quickly, and as we found reasons to build new features, we added the capabilities as required into eBPF.
We extended the infrastructure around eBPF to be able to do things like you weren't able to do before at all in the kernel.
Isovalent and their technology was the biggest user of BPF initially. Their needs kind of determined the path of BPF development, like what features were worked on and what was focused on and where the bug fixes were happening, for example, because they were the ones trying to do new things with BPF and people to actually implement it.
BPF wouldn't be where it is today without Isovalent's help. At that point, we had the kernel changes upstream. In 2017, that's when people started running kernels that could run BPF programs.
There was this famous DockerCon 2017, I think, where for the first time a lot of advocates for eBPF actually by accident were all on the same stage. I spoke on eBPF regarding Cilium, Brandon spoke on eBPF performance troubleshooting, and Liz also spoke at DockerCon. After DockerCon, it was crazy. Like, people joined the community, people started contributing to Cilium and eBPF.
That felt to me like a real inflection point for the cloud native community to say eBPF is going to change the way we build these infrastructure tools.
Every month, the number of developers and users is increasing. We have more questions, more questions on the mailing list and more patches.
At that point, we could see that it was exploding. This is when it really dawned on, like, BPF is going big. People are deploying it. Other people are starting to really use it.
So many new projects that were using eBPF. We could see how it was really influencing infrastructure tooling. It's grown from a big project to a really big project.
All of the major companies were starting to adopt it.
For Cilium, I think one of the huge milestones was when Google Cloud suddenly came and said they had big interest.
Google, as you would imagine, we always have Googlers working on cutting-edge technology. We were looking at expanding our product offering on-premise space with Anthos and GDC. The customer requirements were growing. They wanted more observability. They wanted better network security. They wanted auditing of network policy and network security. We now had to think about how do we really get some of these feature functions fast. It became very clear that with the step function of eBPF, now we can do a lot more. We have a lot more programmability. There's a lot more now security that has been built in. That was the time when we actually were also talking to Cilium folks. It made sense that, there is already a nice stack which works, which is actually having the base that we need and an ability for us to contribute, ability for us to innovate and bring value to the customers. So it made sense at that point to kind of go in and adopt eBPF-based networking stack. Now it's released, it's everywhere, it's on GKE, it's on GDC, Anthos. We have actually made it default on autopilot. So at this point, we are quite stable in where we think the data plane V2, as we call it, has landed.
After eBPF got adopted by the networking to essentially make network programmable and in the tracing, the next was security.
My story starts with a team called Detection and Response at Google. Our job is to prevent Google from being hacked. My manager reached out to me and I said, look, we should try using eBPF. It's the cool, shiny thing, but I don't know how to use it for security or auditing. My job was to figure out, hey, can we write a security language using eBPF?
KP created a framework that he called BPF LSM. He made it happen because he was passionate about using BPF in security.
There was this mentality that security needs to come with the performance stacks, which eBPF's influx into security has changed. They're like, look, we've been doing things in networking that need reliability and they need security, but they don't need to be slow. We can build detection signals using eBPF rather than writing complicated kernel code, shipping it separately, shipping a user space agent separately, and then trying to coordinate the rollout of these two. That's what my life is now.
As companies use more and more eBPF also, it becomes harder for your operating system to not have eBPF because you are no longer eligible to run workloads at Netflix or at Meta or at other companies.
Dave Thaler from Microsoft talked about going to one of the eBPF summits and seeing eBPF and thinking about, well, couldn't we also have eBPF for Windows?
I first heard about eBPF from my manager. The more that I looked into it, the more interesting it became. A lot of the things that we do in our group here, we do have people doing stuff for Linux and we have people doing stuff for Windows. And so when you have things that want to run on top, like an application or something like that, often that dictates common features across them that says, do we have people doing duplicate work? Do we have Windows people implementing a feature and Linux people implementing a feature? Well, that's not great for our company to have to spend duplicate cycles on things. What we like is we like being able to do things once and have it be work across platform. And so the more that we looked at BPF, we said, if this thing could actually work the same on both of them, this would be a game changer. We want the same scenarios that everybody in the BPF world has been using for the last years. And we want those both on Windows and on Linux, both on-premise and in the cloud. And so that's when we first started the eBPF for Windows project.
Microsoft is smart and they know where things are heading. And they've been putting the work into getting eBPF into Windows. And this is a huge turning point for eBPF. eBPF is moving from this cool Linux project to being the industry standard. We realized it was bigger than Linux, that this would be adopted by other operating systems as well, and this should be the standard. And so we created the eBPF Foundation to help facilitate this.
As eBPF is having like a hockey stick growth, around 2020, 2021 is when Foundation really becomes a place to bring together people who are doing this work in different companies and provide that neutral grounds where you can have these technical discussions and drive the impact in the community and create some space to include different voices. So that's how the foundation was formed, with big companies like Netflix, Google, Isovalent, and Microsoft coming together and bringing this to life.
This helps Microsoft come up with a Windows implementation, and in the future it will help BSD come up with an eBPF implementation, and Apple to come up with an OS X implementation as well. So eBPF will be available on all operating systems. I joined Intel in early 2022 to work on the performance of CPUs, GPUs, AI accelerators, and the Intel Developer Cloud. It takes time to take a new product, some new silicon accelerator, and make sure it's properly tuned and configured in an environment. With eBPF, we can do in 1 hour what would normally take weeks. Instead of having to deploy new versions of software with different metrics added and tracing and logging, we can do it on the fly, and we can tell the customer, run this eBPF program and send me the output. I have used eBPF in meetings, where in a meeting someone says, I wish we were able to measure this. And I've said, hold on, opened up my laptop and said, I've done it in production right now, before the meeting's over, here's your answer. And that's the kind of superpower we need so that we can solve all performance issues in days, not months. And to get to the bottom of issues in 5 days means the fastest products get chosen and will win, and the whole industry moves forward.
Today, eBPF is everywhere. We don't realize it, right? In every Android smartphone is eBPF. Most new security products use eBPF. It's really hard to see infrastructure software coming out today that does not have eBPF built in.
We have stats how it is increasing. And what companies are using, we see from emails that people are posting from. Right now, it's every company in the world is using it one way or another.
Even though it's been 10 years, it's still just the beginning of it all. It's not an evolution, it's a revolution. What we saw from the past, that innovation moved further up to user space, we now see the trend that it moves back into the kernel.
It's a really interesting time to be involved in this stuff because, the sky's the limit as far as I'm concerned.
My passion effectively is to innovate and enable others to innovate, and BPF fulfills this role in my life. If in the past the whole kernel would be maybe 100 of programmers across the world, now 100,000 people in the world can program the kernel thanks to BPF.